So again, I just want to welcome you guys to today's 3D Solution Spotlight. This is actually the first presentation from our simulation month, where every Friday for the rest of the month of May we'll be presenting and talking about various topics that relate to our analysis tools. And this week we're going to be talking about qualifying durable products with SOLIDWORKS Simulation and SIMULIA Abaqus. And really what the goal is for that, or for today, is to really look at how we can take your model and what type of results we can get to make sure that the parts that you're designing are going to pass some sort of test or some sort of real life condition where things are not going to break, where we can view that with how far we can get it with our simulation tools, and then when we would need SIMULIA Abaqus to take it to a more realistic, complex setting there. So pretty much the plan for today is, looking at the different studies, or talking about very briefly how we can ensure that we have some durability here within our designs. So what studies can we use to ensure durability? I'll be going over the product breakdown as far as what's included and what we can utilize to really answer that question. But as far as the interface that we're going to show within simulation, SOLIDWORKS Simulation, the webinar will focus a little bit more on these specific topics: linear static, and then linear dynamic, and then nonlinear dynamic when we're looking at SIMULIA Abaqus. So that's really what we're going to be focusing on in terms of how far we can get it within SOLIDWORKS Simulation, and then when we can take it to the next level with SIMULIA Abaqus, which will be presented there with Tim Mila. Okay, so if you've seen our webinars before, I'm sure you've seen this breakdown, but for those of you who are new to it, you see that SOLIDWORKS Simulation FEA is just a branch of many different analysis products that we offer that are all integrated within SOLIDWORKS. So FEA is what we're going to focus on today, but we also have tools to accommodate any type of thermal or fluid type of analysis, or anything that's moving relative to each other, where you want to see certain reactions, where you want to see how much something's going to torque or anything like that within our SOLIDWORKS motion simulation. If you're working a lot with injection molding, and you want to simulate whether your part can fill, whether the thickness of your walls are too thin or too thick, then it'll be able to simulate that within SOLIDWORKS plastics. And these are the tools that are, again, integrated within SOLIDWORKS, but we also have SIMULIA Abaqus, which is of course what we're going to talk about later on in this webinar, where it's again taking these analysis tools that are now we can indirectly communicate within SOLIDWORKS and still get this advanced level analysis. Okay, so and why would we want to use any of our SOLIDWORKS analysis tools? Well, for one thing, if we're talking specifically about SOLIDWORKS simulation or flow simulation with our CFD, then these tools are all integrated, are all part of that SOLIDWORKS family, where they're, if you're already using SOLIDWORKS, then they're powerful, easy to use, you're already familiar with the interface, so it's going to be pretty much a short learning curve to really learn these products. And really the intention of these products is to be a guide to really help you with your designs, right? So that being said, again, it's integrated within SOLIDWORKS, so we can do these fast turnaround times, implement these what-if conditions. What if we need to change, the wall thickness? What happens to my results if I change the material? So we'll be able to do this all within the same interface, where, again, the goal is to get a quick turnaround time. And then hopefully, if you are a customer of ours already, then you are utilizing our tech support. You're obviously checking out these webinars here. Then, simulation, we talk about simulation quite often within our webinars. We have a lot of training dedicated for that. So we'll be your single source solution for anything in regards to what we offer in terms of simulation. So in terms of what do we have available to you in terms of our structural tools? Well, simulation comes in 3 different flavors. We start off with our simulation standard, where that's where we can get in, be able to simulate or be able to do a linear static analysis, where again the results that we're getting from there are stress and displacement according to the assumptions of a linear static analysis, which I'll talk about there a little bit later. But if we're also talking about durability or making sure that things going to, pass the test or withstand, a certain load, then you can also run a fatigue analysis where we can input some sort of SN curve in our material definition and take a look at whether your part or assembly is going to fail after a certain number of cycles. Right? So trying to test not only in the moment, but trying to see whether things are going to pass down the road. And then we have Simulation Professional, which gives us other or additional study types where the results are not necessarily going to be stress or displacement, but still help you and guide you in answering certain questions like how much is something going to vibrate, what are going to be the resonant frequencies of my part or assembly. We can do that with the frequency analysis, but again, we're not really getting how much stress something is going to endure or how much something is going to deform based on a given vibration. That's where we would need to graduate to a simulation premium study, which we'll see later on in our presentation. We can then move forward to a simulation premium, which gives you a more realistic case where maybe it's taking your linear static to the next level where you now need to define what's going to happen post-yield. You need to get more accurate results in terms of what's happening within the plastic range of a material curve. We can do that with the nonlinear. And then we can go pretty complex where if you're simulating something in a shaker table or you want to account for some sort of seismic loading, then we can do that within our linear dynamic studies, again within Simulation Premium, which will give you everything you see on your screen here. Okay, so if we were to narrow this down to product, then if we are looking at SOLIDWORKS Simulation Standard again, we always want to start off with the linear static assembly or linear static study. And the thing to be aware about that is the assumptions that we take within that is the material that we're looking at or that we're going to apply to our parts are always going to behave linear elastically here. So we have no way of us defining what's going to happen within that plastic range or post-yield. So we assume that the displacements we're going to see are going to be small versus these large displacements where things may be going into yield. So we can't account really for permanent deformation within the linear static. And then we also assume that the loads are applied slowly and gradually, meaning that we can't apply any fast or any shock type of loading within simulation standard or within our linear static. So the inputs that we apply for that are, of course, some sort of linear material definition, and then we apply some sort of restraint and some sort of load or gravity or prescribed displacement to actually deform the model. And then the results that we get are, of course, stress, displacement, strain, and factor of safety. So how does that look? So the model that we're going to be looking at here throughout this presentation is going to be this electronics box where, maybe I do have some sort of dynamic testing that I want to do, but, all I really have is this linear static. Well, how far can I actually take it within this software or within this first level analysis? So you see that I already have something defined already. And really what you're looking at is when you create a new study, you're always looking at this interface here where we really go down the list and start setting up this definition of study. So you see that this assembly consists of all these parts. When I go into the material, again, we're assuming a linear elastic material here. We're utilizing the database within SOLIDWORKS here, and it's incorporating all these properties to really give us what those results are, which is stress and displacement and strain. So we apply those material definitions for all the parts, letting us know that we've defined one based on the green check there. And then we can define, how things are going to be interacting with each other, whether things are going to be bonded or things are going to be able to separate from each other. We tell the software how that behavior is going to be, whether things are already touching or things will come into contact. And then later, or after that, we then define how something is going to be restrained. In this case, I'm assuming that this electronics box is attached to something that's going to be, either exciting the model or applying some sort of load onto the model, where in this case, I'm just defining some sort of gravity. So I'm assuming, what's going to be the dead load or what's going to be the load if I were to increase that acceleration, where in this case, I'm pretty much saying that there's going to be an acceleration going in the downward direction, pretty much 5 times gravity. So 5G is being implemented within this electronics box. You see that I have the option to define different directions of where this acceleration is going to be applied. So we could get some first level type of acceleration type load onto this assembly and still get the results like stress and displacement, of course, if we're within the guidelines of what a linear static assumption offers. So after we mesh our model, right, we break down the model into these small elements here, and then we run the analysis, and we get something like stress. So you see, with just a linear static, we can get pretty far in terms of getting some first level estimation as far as what's going to happen if I were to apply some sort of 5G acceleration onto my model into whatever direction that I want. And how we would interpret these results are, if we're looking at the max stress, where does that fall within the yield strength of the material properties? So if I'm exceeding that yield strength, then that means that something has yielded or something is going into post-yield where a linear, those max stress results are probably not going to be as accurate, where I can make the assumption though that maybe something is breaking or maybe something is reaching a high stress where I need to do some sort of design change. Right? So I can take a look at this and let us know, or it can show us, is this deforming too much? Right now we're looking at an exaggerated case where the deformation scale is set 1,600 times, but we at least get an idea of how things are going to be deforming. Right? And now we're looking at a displacement plot where I can actually animate this and see, based on that acceleration that I define, how is it going to deform? Well, what are the things that I might be concerned about, maybe some of these components here. Right, so with the linear static analysis, again, we're all integrated within SOLIDWORKS. A couple tabs away, I'm within my actual model where I can then go back and adjust something about my assembly, either change the design, change the layout, and then I can go back into my analysis and rerun it and see how those stress results change. Right, so that's how we would take that approach within a linear static. Moving forward, we can then take this to a nonlinear study within Simulation Premium, where in a linear static, I mentioned if things are showing that are going, above yield, then those stress results are probably not going to be as accurate as if we were to compare it with a nonlinear study. Right? So within a nonlinear study here, you see that it's the same setup in terms of defining some sort of material, but now we can input a stress strain curve, what's going to happen at post-yield, and this time we can account for this large deformation, so we're getting a true representation of how the stresses are going to be seen when we have this large load or this large acceleration that we're applying onto our model. We can also account for any contacts or loads or fixtures that are changing as things are deforming, which is something we wouldn't be able to do in a linear static analysis. Right, so I don't have anything set up too far in terms of the actual setup, but you see that the overall setup is the same. It's still restrained there. I still applied that gravity load within our nonlinear. But now looking at this nonlinear study, if I were to look at some of my parts, now when I go into the material definition, we're not using a linear elastic material. We're now able to define this plasticity von Mises, where it allows us to find this stress strain curve. And again, I utilized a material that was from our material database, where if I had something a little bit more unique, I could have customized or created a custom material. You see this material has a dedicated stress strain curve. So if the stresses reach that yield point and beyond, the stress results are going to be more accurate in terms of what's happening within that range. Right? So really, again, what I'm trying to show you here is the different capabilities that we have available to really test these different scenarios so you can be a little bit more confident in your design. Right? So if we had something a little bit more complex where we wanted to take that acceleration to maybe in real life you're actually testing your part or assembly within a shaker table, or maybe you actually wanted to account for some sort of seismic behavior. Maybe that electronics box is going to be attached to something where we're concerned about an earthquake, right? Or maybe the thing's attached on a truck where it's running through a bumpy road, and we want to see what those stresses are based on those random interactions, based on that random vibration. We can do that with these dedicated linear dynamic study types here. So it's a way to analyze how the design is going to respond to a loading condition that essentially changes with time. And we can implement these really complex scenarios within these study types here. The first one that I'd want to talk about is a response spectrum analysis, where, again, it allows you to define this virtual test based off this shock response spectrum data where, again, we're simulating some sort of seismic behavior, right? So we can input, we can download this information here where, I found a curve from the U.S. Geological Survey website. They give you what those load inputs are, or maybe you're working with some sort of military where they're giving you some sort of mil-spec standard where they're telling you what that seismic behavior, what that load input is going to look like. And again, the inputs are going to be very similar, where you have to apply some sort of definition, you have to apply some sort of restraint, but now instead of some sort of load or pressure, you're inputting that response spectrum data. Usually it's going to be some sort of acceleration or velocity versus frequency. And then the unique thing about the results is that we're getting what the peak response of the stresses, which means the worst case scenario or the max response of stress and displacement based on this seismic behavior. So switching over to this response spectrum analysis here, you see that, again, very similar to a linear static, where I define my materials, I define the context between these components, define the fixture in the same location, but now my load, not only do I have the option to input some sort of prescribed displacement, I can define this base excitation where we're defining what type of load input do I have. The data that I got from the website was, some acceleration as a function of frequency. So I can say what direction, that acceleration is going to be applied. Again, you have options to define multiple directions as well. But then as far as how I'm going to vary that is, based on these frequency data, these are going to be the multipliers or the amplitudes at that given direction here, right? So when I input that data here, I can run the analysis just like normal. And again, the results that we're getting are the peak responses, in this case, for the stress. So we're looking at that worst case scenario, that worst stress scenario based on this load input, where I can animate this as well. And essentially, we can see it just kind of vibrating up and down due to this seismic behavior. All right, so again, we're looking at the peak response. And in this case, if we're determining or trying to be familiar with the seismic behavior, that might be enough. That might be what we need to learn from this. But we don't see how these stresses are being developed from it just sitting there to it being excited. So the next level up to that would be to do some sort of maybe time history analysis here, where it allows you to do, again, this virtual test of now maybe implementing some sort of shock load, where the load that we're applying is happening at a very quick time, a very split second there within the model, where maybe we're representing some sort of like impact, where, again, we can get that data from some sort of mil-spec or whatever standard or whatever scenario you're running, where, again, now the main input here that changes is that loading is changing as a function of time, where the results are now back to stress displacement, but we can see how those stresses and displacements are changing as a function of time, where we can then take a look at the response as well. So if we take a look at that time history, and the nice thing about these linear dynamic analysis is that once you're familiar with one type, the overall setup is essentially going to be the same. Where you notice the setup is the same here, except my base excitation input is not a function of this seismic curve anymore. Now it's going to be a function of time. So in the same case, I am applying this acceleration in the downward direction. I am putting some sort of 20g acceleration there. Excuse me. But you see, as far as the shock input, you see that I'm defining a time curve where that shock is happening at 11 milliseconds. So it's happening very quickly, and I want to see how the stress behavior gets affected based on this very quick impulse shock load. So when I run the analysis, I can get my stress. if you point your attention to this cloud message here, you see that I'm looking at the stresses now at 0.019 seconds. I can go into the stress results and view the stresses at any time increment that I define within here. So if I do it at 11 milliseconds there, then you see that I can get my results there based on that time step, or again, I can animate this and you see how the results are changing as a function of time. Right. We can take a look at the displacement results as well, right, and animate this and see how much is deforming, is anything colliding. Again, these results are amplified so we can actually see how the results are deforming or how the parts are deforming. But then we might be interested in specific location. Maybe we're interested in the transformer or the heat sink there. We can define a response graph at specific locations of the model, and you see how much is that deforming as a function of time, right? And we can define any type of response here, where if we go into response graph, we can say, you know, at predefined locations or at specific nodes or vertices within the model, I can view the stresses, displacements, acceleration as a function of that time. So we have full knowledge as far as what's happening at specific locations in terms of what is our worst case scenario based on this time frame here. Right? So a lot of good information in terms of how the stresses are being developed as a function of time. And then lastly here, you know, very similar to a time history, maybe your load input or maybe what you're doing in real life in terms of testing is the shaker table, then where your input definition is some sort of vibration across a range of frequencies, then that's going to be the load input that we define here, and the results that we get are going to be very similar to what we saw in a time history, where if we look at that basic citation here, you see now in this case still loading at 20 Gs in that direction here, in the downward direction, but now my load input is going to be a constant frequency range from 0 to 2001. So we're seeing this, you know, operating range being defined here. This is maybe what we're seeing or what we're testing in the real test picture of the shaker table. And then, of course, the results that we get are now the stresses as a function of that frequency, where, again, I can animate that and see, you know, as the frequency is changing, you know, how are these things deforming, how are they stressing. We can do the same here with the displacement, or we can, again, generate a response graph where we're interested in at specific locations or a specific location within the model, and we can see how much does this deform and specifically at what frequency. So at that point, you can answer the question, is that a concern? Is this meeting my criteria? Is that meeting my standard? You know, is this okay or not? If it's not okay, of course, then you can go back to SOLIDWORKS, do some sort of design change, or change something about the overall model. So that's pretty much what I wanted to show you in terms of, you know, what we had available to us within SOLIDWORKS Simulation, how far we can take it in terms of the results, you know, from a very basic linear static analysis to a very complex dynamic analysis. But now I want to switch it over to Tim Milo, who's going to talk about how we can take this to the next level with SIMULIA Abaqus.
Thanks, Silvio. So I'll go ahead and change me to the presenter, and I'll take you guys through some information about what SIMULIA Abaqus is and when it's a good fit for your engineering problems. So Abaqus is an expert level tool in a sense that you have a lot of choices into the material calibration, the failure properties of materials, and a lot of pretty powerful contact choices. In the few examples you see on the screen here, in the far right, there's a crash test with a pole where BMW has basically gone towards fully virtualized testing before they do early prototyping. And then another key thing to highlight is that in these other contact analyses, we have a lot of self-contact and some high deformation going on in the metal. So I think those are kind of key areas where you'll find that Abaqus comes into play. It's used across quite a few industries for sort of those same reasons. Complex material models, like you can see in the industrial equipment example, or complex contact and some failure capabilities like fracture mechanics that you'll find more in aerospace. So that's the kind of broad overview of when people tend to bring it into their analysis workflow. SOLIDWORKS is a bit more integrated where you're directly in your CAD tool with your analysis setup. So they each have their time where they are more applicable. So I'm going to walk through the basics of setting up an analysis in Abaqus. The general workflow is that you'll bring in your geometry from CAD. You'll set some material definitions, mesh, choose what type of study you're doing, tie the parts together, apply your loads and boundary conditions, and then do your run and post-process. So in the example here, we're looking at the phone drop that you saw on the previous slide where your initial boundary condition is that it's got an initial velocity towards the floor. In that one, we'll choose from material models. So in the case of, for the phone case, we have some test data that we can test the fit of a few different rubber models to. And then in the glass, we can choose whether we want the elements to just lose shear strength, which is what you see on the right of this animation, or whether you want them to actually develop a crack fully through and disappear when they don't have any more connection to the model like you see on the left. And then last, in this analysis, I pulled in a stress strain curve from the SOLIDWORKS simulation tools, and that's part of the workflow that I find pretty handy is that I'll go to the library and pull it out if it's doing a material that's already in that. Since SOLIDWORKS has a full database built in, with Abaqus you can build your own central database of materials, but since I end up working with a lot of different units with the models, I'll tend to just find them from the source as quickly as I can. And then the last piece that I'll sort of touch on is that you have a bit of control about how you mesh things finer in a spot or coarser in a spot, and this is always part of the strategy with an analysis, is figuring out which parts you care about and where you spend your computational effort. So that's a quick overview of what I'm going to get into here. So what I want to do is show you the import and the workflow to go into Abaqus from SOLIDWORKS. Have the sort of familiar electrical box problem that Sylvia has been digging into a little bit. And what I'm going to do with that is, since it's bolted to the floor and we're not likely to drop it, I'm going to go ahead and drop something on it in this example today. So first thing I do is pull in the geometry from CAD. You can see I have it, in this instance, I have it right over that corner, so we'd expect, we're probably going to do some damage to those mounts and that sidewall. These take a bit to run, so I'm going to just go ahead and go right to what those results look like to give you an example of our end product. And so I've got my deformation scale set up pretty high. With explicit runs, you'll see quite a bit with just a 1-to-1 deformation. So if I go ahead and animate that, you can see that first of all, it's a very short duration event. It's more or less over by 0.03 seconds. But you can see we capture quite a bit of plasticity and damage along that wall just where it hits. And you can even sort of differentiate the edge of where the extinguisher hit from the center where it's indented. So if I turn off the mesh gradient, we get a little clearer picture of that. So from here we could do things like we can pick a node inside and take a time history. We can hide the lid so that we can see what's going on inside of it. This one I happen to run it on an empty box, kind of an early setup and test. But you have all the capabilities to pick any node and generate a response spectra or do some other types of math on that. I'm going to go back into another setup. So skipping from just importing the CAD to sort of first steps to see if this model is connected. So I went ahead and I mentioned the first thing you do is pull in your parts. So we have all the unique parts of the assembly. And then the next thing I do is define some material properties. So the workflow in Abaqus is sort of dictated by the module that you're in. So you'll drop down through the modules and complete them as you go. So I just pulled in some aluminum material data from SOLIDWORKS. We have a few choices around failure mechanisms, damage for ductile metals, or we have brittle cracking and other options if we're in glass or in concrete. And I think I just have kind of a generic elastic silicon model, which is fine, and then a PCB model where we just define a density and a modulus. So once we set those things up, what the property module does is it lets you map the material property to a part. So essentially this is where we say what type of element it's going to be. In this one I defined a thing what is called continuum shells, where you use a shell element technology, but it determines the location of the shell based on the surface of the material. So it's kind of a novel, a unique element type to Abaqus, but what it allows you to do is sort of quickly set up these parts with aspect ratios that are better for shells, in that they're a lot of element. The scale of the model is such that you have a thin plate that's very long, and to mesh adequately through it, you'd either need many elements to get a few elements through the thickness and capture the length appropriately, or use a thing like continuum shells. So once we've imported those parts and we've gone through and mapped material properties to them, and we can see, we can either map it by material and look at what we've defined that way, or by section. We have a few options there, and we've imported them all into the assembly. The next thing to do is choose a step type. So this first one, I wanted to use a frequency analysis, and basically what I want to do here is say, okay, did I get everything connected in the model? So we've chose our step type. We come to the loads, and basically I just apply fixed at the feet of this, where it's bolted to a floor or a cabinet or what have you. And the next thing is in the interactions, what I've done is go through and create some ties between these unique components. They're not necessarily sharing nodes or meshed together as I mesh this whole thing. So we have some choices around that, but basically what I did is use a module where I'll come in and I'll find contact pairs, and we have some settings here for what type of tolerance, and do you want to look across the whole model, or do you want to sub-select some portion of it. But then I've just created a series of ties between some surfaces. You could do meshless connectors that have a break strength if you prefer. There's a few different options there. But yep, what I've done is tie these together. And once we define our study type, tie everything together, set our boundary conditions, and we've got a mesh, we're ready to run. So I'm not going to run it right now. The frequency analysis actually does run quite quickly. But what I'm going to do is just come down and again just kind of preview some of the results. So we can hide a piece and get a look inside, and then again we have pretty significant scale factor on the deformation, so we can see what's going on. But we can step through these modes, and everything is definitely connected, so we're confident that our model at least has connectivity across all the parts. That's a good sign. So then if we come back to the assembly, and I want to take a look at what might happen if I say we want to do a drop test on this, we have an add-in module where we can essentially set the angle to the floor and an initial drop height, and then we'll just go ahead and set that drop up. And what that does is give the whole thing an initial velocity and say it's going to hit the floor at a 45-degree angle. Usually you may go a bit steeper than that. Usually the worst case for a drop test is center of gravity over corner, but I think it gives a nice kind of picture of what you might do with the drop test module, qualifying your components. Another assembly type or another analysis type that I set up was a basic static. Not too much to get into there. I'll just kind of highlight that we come in and we define a gravity. Our units are in millimeters, so it's a fairly large number to look at that acceleration for people that are used to working in meters or feet. And then kind of similarly, we have a shock test. I should mention all these models is in simulation, where you're across the bottom of the screen. they're arranged across the left of the screen in Abaqus. But if I come into the simulation for the shock, we can see that I define an amplitude, and in this case I just sort of waited for Silvio to work out all the details and copied the homework, imported the amplitude there, and again we have the same sort of visualization capabilities in here. We can come in and pick an acceleration at any one node. Thank you. And we can plot that through time. We have the ability to do Fourier transforms on those if we want to create a spectral acceleration. So we have some post-processing capability in here that's pretty nice. So walking you through those things, I'm going to go briefly into what's different about the explicit dynamics analysis with the drop of the fire extinguisher. With this one, I went in ahead and I changed the part type of the extinguisher to what we call a discrete rigid. So what that means is that it's meshed externally for the purposes of contact, and it's got a mass applied to it. Once we go into the interactions and we look at how I set up contact, I use a thing called general contact, where you just click a button that everything is detected to have self-contact. And what that means is, beyond tying all the parts together inside, we just automatically detect which parts may fold onto themselves in the case of local buckling, or when they'll interact and contact each other. So I'm going to do a cut view of this so we can see what's going on inside. And then if I plot this time history here, you can see the extinguisher will impact that, and the components inside get jarred around a bit. I'll let this play a couple times just to give you a sense of what that visualization will look like. So those are the main types of analysis that I wanted to go through showing you in Abaqus today. You know, everything based around the same box configuration, whether we drop the box, drop an extinguisher on the box, or we use the drop test configuration to sort of generate an automated drop test from one of our model configurations. You know, a bit more complexity in the workflow in terms of choosing all your material failure models and things like that. So it definitely takes a dedicated analyst type of a effort, but you can get some pretty powerful visualization results out of the tool. So going on from that, I want to cover our simulation services offerings a bit. We have a team of guys that are dedicated to doing your analysis problems as consultants with Hawk Ridge Systems. We offer it in a few different ways, whether we do half-day mentoring sessions where we sort of bridge the gap between what you come out of a class ready to do and some sort of industry knowledge about the way the tools are used. You know, we do a whole lot of electronics cooling work, some different structural analysis, whether it's we'll take test data and develop analysis to replace destructive testing, and thermal and all types of SOLIDWORKS flow simulation problems. So definitely, if you have needs that aren't met in your simulation portion of your engineering workflow, this is something that we can step in and help with, whether it be mentoring, developing your first approach when you purchase a software package, whether that's SOLIDWORKS Simulation or whether it's Abaqus. That's something we got a team of guys that are dedicated to serving you there with. So with that, I'll give it back to Silvio, and we'll have some time at the end for any questions about the Abaqus workflow that I covered, services, or the SOLIDWORKS simulation workflow as well. I would take a quick moment to ask a couple questions about what you're doing in stress analysis currently. So if you'll bear with me, I might ask how often you use analysis tools. And let's see, Silvio. Oh, it looks like we've got our attendees And it looks like we got a decent response already. We've got almost half the audience has weighed in. And it looks like quite a few of you use it weekly and quite a bit, another chunk of you use it every day. So that's interesting. So now we'll ask a question about which tools that you do your analysis in. So yeah, please, if you can, tell us anything about which tools you use in your workflow. And this time we got some pretty quick respondents and definitely a strong SOLIDWORKS simulation showing. All right, so we're up to about half respondent, and that's good. And I'll trouble you with one more, which is to ask when you go to the effort of doing analysis. Are you looking at things from a sort of a early in the design process, or is this for failure analysis post-mortem? All right, great. We got almost the whole class in. Thank you guys for that.
All right. Well, thanks, Tim, for all that great information within SIMULIA Abaqus. Let me switch it over to my screen here. Give me one sec.
Yeah, and thank you guys for weighing in on these polls. It's always good for us to learn about how these tools get used.
Hey, Tim, can you switch it over to me, actually?
Oh, yeah. Sorry, bear with me here, Sylvia.
No worries.
All right, guys, sorry for the delay there.
All right. Thanks, Tim. Back to me here. Just want to, again, kind of recap on what we showed you here. It's a lot of information in terms of the analysis tools, and really what the goal that we wanted to really achieve here with this presentation is really letting you know that we have a large range of different ways to handle any unique problem that you are really facing with your design within SOLIDWORKS or maybe any other CAD tool here. But the software is just one factor of that, and sure, we can provide the software to you, kind of recommend what the best tool for you is, but we also are there with you, post that situation as well in terms of helping you really learn the software and how we can incorporate what your real life testing is and how we would demonstrate that within simulation. But some of the resources here, starting from the top, is within our website. If you go to any of our product pages, there's direct links to our YouTube channel, which has a large number of different simulation or analysis videos, web blogs as well. There's a lot of great resources there where you don't even have to deal with a sales rep or anything like that. But moving forward, if you did need something a little bit more one-on-one or a little bit more help in terms of the software's not working okay, or you're not really sure where something's located within your simulation, that's where tech support comes into play, which if you have subscription with us, you have full range in terms of the type of support we have to offer. And then of course, with any simulation product that we sell, we do offer training within this as well. We have a dedicated engineers to help you or to teach this material for you to get a greater understanding as far as how to utilize the software, how it's integrated within SOLIDWORKS, and really help you achieve the results that you're trying to get based on your real-life testing. And then, of course, if there's anything that we don't cover within the class, or if you need even more dedicated time within that, we can go into that mentoring consulting where what Tim was referring to, where we can utilize our degreed engineers, utilize the software that we have available to us, and help you either do the work for you or spend a little bit more one-on-one time in terms of helping you set up these different problems. So this kind of concludes this week's presentation here. Again, this is Simulation Month, where every Friday we'll be talking about different products within the analysis tool set here. Join us again next Friday, May 19th at 11 a.m. We'll be joined by Damon Tordini, who is the product manager for flow simulation, who will be talking about thermal and fluid performance within flow simulation. And then we'll end the month with talking about manufacturing process, which we'll get into our SOLIDWORKS plastics tool on May 26th. To help you with any additional information, feel free to go into our website or hit up any of your direct sales rep or technical support, and they'll be able to guide you in the right direction in terms of clarifying any questions that you may have regarding our analysis tools. Okay, well, again, I just want to thank everyone for joining us today. If you have any last-minute questions, feel free to submit it through the chat, and we'll be answering those shortly here. Okay, thanks everyone, and have a good weekend.